Se introduzir nos mistérios do mundo mineral é tentar ver no presente os vestígios de um passado distante. É investigar como detetive essa história que começa a se revelar ante nós, proporcionando algumas respostas, mas, sobretudo, muitas perguntas.
Main goal for a geologist, just take the name, or the etymology of the word. Geology is the study of the earth. So logia, logos, is the same word that from the Greek means intellect or understanding or word and reason. So the dialectic component, the ability to frame a hypothesis and to express that hypothesis, and the intellectual component, the ability to create a logical framework, organized logically your set of observations and data. And the earth is really the context in which you are putting this effort, within the context of understanding our planet. So for a geologist, the goal is to make sense, to organize, to find a common thread, to find patterns, to find sense, to find meaning, to find organization, to find design also in what we observe on planet Earth.
The Earth is made up of rocks. The core of the Earth is made up of one kind of rocks, and then there's the mantle and the crust. So the entire Earth is made up of a variety of rocks, but we think most of the rocks at the surface. So a lot of the time, geologists are looking just at the different kind of rocks at the surface of the Earth. And there's different environments for the different rocks to form at the surface of the Earth. So one kind is if you have liquid rocks that come up from the interior of the Earth, they come up to the surface and come out. And so everybody knows about those. At volcanoes, you get lava that comes out. So that's one kind of rocks. Now, if the liquid rock, if the magma comes up, but it doesn't come all the way to the surface like a volcano and stops underground, maybe several kilometers underground, then it cools slowly and you can get large crystals, and those large crystals you can see in granites, in granitic kind of rocks. Now, those volcanic rocks and granitic rocks are called igneous rocks. Another kind of rock is a metamorphic rock, and that's where the rocks are hot, but they don't get hot enough so they're liquid. They're just hot enough so that they're plastic and they can fold and different minerals can form. And so metamorphic rocks are rocks that are formed under high pressures and temperatures. One example of that is marble. Another example that you might be familiar with is slate, which is a rock that has been heated up just a little bit and some of the minerals have changed. Then the third kind of rock is a sedimentary rock. A sedimentary rock is probably the kind you're most familiar with, and it forms at the surface usually by water, by the action of water. Sometimes by wind, but most of the time by water. And so if you have water carrying along sediments like sand, and the sand is deposited like on a beach, and then it gets covered up, the sand can turn to sandstone. So that's a very typical sedimentary rock. If you have very high energy environments, then it can carry pebbles or boulders. and then you'll get a conglomerate. So a conglomerate's another kind of sedimentary rock. If the water is not moving very fast at all, or if it's not moving, then you can have the mud in the water will gradually settle out to the bottom, make mud at the bottom, and then over time that mud can harden into rock called shale. So those are various kind of rocks that are called clastic rocks that are due to water carrying particles along. Another kind of rock are chemical rocks where you have material precipitated out of the water. So if you have something like calcium and carbonate precipitated out of the water, then you'll get limestones. And a limestone is a very common sedimentary rock. Another kind of chemical sedimentary rock is what are called evaporites. If you have all of the water evaporate away, then whatever minerals are left in the rock get precipitated out. For example, ocean water has salt in it, but if all of the water gets evaporated away, you're left with the salt, and you'd have a salt deposit. And so there are various places where you have sedimentary formations that are salt. Another one is gypsum. That's another kind of chemical precipitate.
Os três grandes grupos de rochas encontrados na superfície da crosta terrestre, rochas ígneas, sedimentares e metamórficas, estão distribuídos de maneira diferenciada na Terra. Por exemplo, a crosta como um todo, 95% da crosta é formada por rochas ígneas e metamórficas. Então, em termos assim volumétricos, a crosta realmente, a rocha prevalecente seria rochas ígneas e metamórficas. Já na superfície da Terra, aquele material exposto na superfície, a maior parte são rochas sedimentares, que ocupam mais a superfície da crosta. 75% das áreas continentais estão cobertas por rochas sedimentares.
Componentes inanimados da estrutura que nos rodeia, agentes dinâmicos que sustentam um contexto onde nos movemos e somos. Um ambiente próspero, cativante, cheio de vida e interações, das quais somos parte e desfrutamos. Desde a água até as rochas, desde os vales às montanhas e dos profundos oceanos até o espaço, por onde quer que observamos e encontramos geologia. Esta ciência da Terra que, acima de tudo, nos proporciona um ponto de referência para compreender o passado, presente e futuro deste maravilhoso planeta, o qual chamamos de lar.
Para os geólogos, o material acessível de maneira direta são os materiais que estão na superfície da crosta terrestre, ou seja, uma camada de mais ou menos 200 km de espessura nas áreas continentais, e nós conhecemos apenas a parte superficial. E ao estudarmos essa parte superficial, nós vamos identificar três grandes grupos de rochas: rochas ígneas, sedimentares e metamórficas. E essas rochas, por sua vez, cada grupo desse é subdividido em outros tipos de rochas. Praticamente, cada dia, quem sabe, um novo tipo de rocha é descoberta. Agora, existe outro tipo de rocha, aquela que é mais abundante na crosta, as rochas ígneas. Essas, quando se formam na superfície, porque a rocha ígnea é produto da consolidação de um material fundido, rochoso, que no interior da crosta recebe o nome de magma. Esse magma, quando atinge a superfície, passa a ser lava. E essa lava, em contato com a atmosfera, ela se resfria, se cristaliza e forma as rochas ígneas. Uma das mais comuns são os basaltos, né? E é interessante que é nesse momento que eu consigo fazer comparações melhores do presente com relação ao passado. Porque as rochas vulcânicas que se formam hoje, a lava praticamente é a mesma que formou as rochas vulcânicas do passado. Então, se existe um tipo de rocha que se forma hoje e permite fazer uma ponte com o passado, são as rochas ígneas, extrusivas ou vulcânicas.
Em poucos lugares do mundo, a geologia e a história da humanidade estão tão intimamente ligadas ao vulcanismo como na Islândia. Graças à sua localização estratégica sobre um ponto quente, o hotspot vulcânico sobre a dorsal mesoatlântica, esta peculiar ilha no extremo norte do planeta surge e se renova geologicamente por meio de poderosos processos vulcânicos ativos que sucederam e ainda sucedem em todo o seu território. Segundo medições globais mais recentes, 1/3 de toda a lava expelida sobre a superfície terrestre, desde os primeiros registros destes eventos na Idade Média, corresponde à Islândia. Isto sem contar as erupções marinhas, as quais são ainda mais extensas do que as que ocorrem em terra firme. O que será que podemos descobrir investigando os vestígios das inumeráveis e extensas erupções que esculpiram, com o passar do tempo, as extraordinárias paisagens islandesas?
Okay, so one thing I do when I'm mapping here in Eastern Iceland, I use the structure of the lava flows to tell me about their preservation. And this is an interesting place because we see the very contact of the lava flow with the welded tuff on top. And this contact here, as you see this lower part here, is actually the very upper part of a lava flow. And you could see it by the vesicles. The very upper part of the lava flows has, vesicles in it. And as you get to the very top of it, the vesicles get smaller. So this just means that this lava flow is perfectly preserved. The very top of it is preserved. But the next thing that happens is that this tuff is deposited on top of the lava flow. Now, I don't have the exact time here, but it could be actually that these two deposits, both the lava flow and the tuff, were erupted relatively rapidly, in rapid sequence, because there's seemingly not much time here. If there was much time, usually weathering eats the crust of the lava flow. It is the top of it is very vulnerable to weathering. So it would degrade and form a soil section into the crust. But we don't see that here. And actually, in most of the lava flows that I've mapped, the lava flows are perfectly preserved, suggesting rapid deposition. Geologists have at least two ways of identifying time. One is through radiogenic elements that have a half-life and they get thousands and millions of years by dating rocks. Another way is to look at the rocks themselves and to see what are the rocks telling me and what do the processes that form these rocks, what do they tell me about time, about the sequence of events and so forth. And I personally am very interested in the story that the rocks are telling me and actually how they correlate with then these other clocks that we geologists use. And yes, certainly in my view there is a problem there to be solved, because there's not much correlation always between the story the rocks are telling me and then between these radiogenic clocks.
Uma incongruência que desperta dúvidas, um alerta que nos relembra os limites do conhecimento e a constante científica inevitável da incerteza. Mas na realidade, a grande pergunta é: estaremos prontos para ver e interpretar a verdadeira história que nosso planeta tem para contar?
As you study geology, you're studying various processes, and as you study the processes, you need to have a picture of the sequence. What happened first? What happened next? What are the causes? What are the effects? So you need to know the order of events. If you want to study the relative time between rocks, if the rocks are close to each other, you can see how they're related to each other and probably figure out which came first and which came second. However, if the rocks are a long ways apart, you have some rocks in Europe and you have some rocks in South America, how do you figure out what the relation is in time between those rocks? And so geologists have developed a technique for determining ages for rocks that are a long ways apart. And that's radiometric dating. That looks at the atoms in the rocks, radioactive atoms. Uranium is radioactive, it decays to lead. Potassium is radioactive, that decays to argon. Rubidium is radioactive, that decays to strontium. And so if you count the number of parent atoms, like uranium, and you count the number of daughter atoms, like lead, you can figure out the ratio between them and figure out how long it's been decaying. And so this is one of the most popular techniques that geologists use to find the ages, the relative ages between different rock units, and what happened first, what happened later, what's the cause, and what is the effect.
Existe uma variedade de aplicações, mas o princípio básico é sempre o mesmo. Existem tipos de átomos que são instáveis. Eles tendem a se transformar em outros tipos com o passar do tempo. São átomos como, por exemplo, carbono 14. A gente não usa isso para rochas, mas a gente usa para tecidos vivos. Existe o estrôncio 90. Esse sim a gente usa para rochas. Existe o argônio e potássio. Existe uma série de elementos, argônio e potássio são dois elementos químicos, mas a gente costuma usar esses dois em combinação num dos tipos de metodologia de datação. E quando a gente faz essas datações, existe uma margem de erro mais ou menos grande ali. Tipicamente, o pessoal fala em 5 milhões de anos, é uma margem de erro normal. Fora isso, a medição parece muito precisa. O que é preciso? Preciso, o conceito de precisão nesse caso, indica reprodutibilidade, ou seja, eu meço usando algum elemento químico, uma estimativa de idade de alguma rocha, faço uma estimativa de idade baseado em algum decaimento radioativo, faço baseado em no decaimento radioativo de um outro elemento, e os resultados são parecidos, sempre parecidos. Existe o problema, por exemplo, das condições iniciais também. Como eu vou fazer uma estimativa do tempo que demorou para chegar até as condições atuais, se eu não sei as condições iniciais? Então existe um método que resolve esse problema, que é o método das isócronas. É um método que a gente coleta amostras e cada uma dessas amostras existem quantidades de elementos, proporções de quantidades de elementos que a gente mede ali. Resultado a gente coloca num gráfico. A inclinação de uma reta que se forma nesse gráfico nos dá a idade da rocha, sem precisar saber de condições iniciais. E esses números também têm uma precisão bem interessante. E mais, tem um método de autocorreção, que se a minha amostra é ruim, os pontos não param exatamente em cima de uma reta. Quanto mais incontaminada, vamos dizer assim, está aquela rocha, mais os pontos se alinham. Então parece o ponto perfeito. Então eu vou medir uma rocha muito antiga, por exemplo, eu posso obter resultados como 2 bilhões de anos. Existem até rochas mais antigas do que isso. E esses resultados têm precisão, ou seja, eu meço com um método da 2 bilhões de anos, meço com outro da 2,1 bilhões de anos, outro da 1,9. Então estão próximos um do outro. Agora, será que esses resultados são exatos? O conceito de exatidão é diferente. O conceito de exatidão tem a ver com proximidade da realidade. Eu posso reproduzir um resultado muitas vezes e esse resultado tem um viés intrínseco que vai me desviar da realidade. Como a gente faz para resolver esse problema? Aí nós precisamos de métodos não baseados em radiação, métodos baseados em algum outro tipo de fenômeno.
Estudar a história escrita nas páginas rochosas que cobrem nosso planeta é muito mais do que revelar um contínuo registro de processos. Nelas, podemos também identificar formas passadas de vida, complexidade, evidências de eventos dinâmicos e catastróficos e, inclusive, tendências que podemos estudar e entrelaçar para obter dados mais precisos sobre o tempo transcorrido desde sua formação. Mas para compreender plenamente toda essa informação, devemos estar atentos. Afinal, são vários os conhecimentos necessários e os dados são ainda mais extensos que a própria superfície da Terra.
One of the most critical issues that we have to face as geologists is the question of time. Most geologists are absolutely certain that the world as we know it has been here for billions of years, and that life has been on the earth for hundreds of millions of years, and that these processes have been going on through all that time. When we read the story in the Bible, we realize that that is inconsistent with what we read there, that the Bible is giving a very different picture of life on the earth, that it's been here for a few thousand years and not for millions of years, and that this is a constant part of the whole story of the Bible. Then we have to go back and reevaluate things, and when we do that, we find out that we overlooked some very important features. For example, we find out that if sediments had accumulated slowly, like geologists would want them to, they would be accumulating 1,000 times slower than they are today. And today we don't see anything spectacular going on. We just see normal processes, but the rate of accumulation is about 1,000 times faster than the rates we get if we use radiometric dates for the accumulation of sediments. So how do you explain that? Well, that's one thing you see. Another thing you see is that the sediments themselves don't appear to have been subjected to time, because if you lay down a layer of sediment in the ocean and it has internal structure that you can see, and then you leave it there for a day or a week or a month or a year, and you come back and look, you'll find out that animals have burrowed into that sediment and have destroyed all the internal structures. So it doesn't take very long before sediments would no longer talk to us. They would no longer have the information that sedimentologists need to understand the sediments. And yet when we look at the rocks and we see the layers of rock, we can see inside and we can read the story that they tell. We don't see evidence for time. What we see is that one layer is deposited, and then before it can be disturbed, another layer is put on top, and so on. And very seldom do we find any extensive evidence for a period of time. So this is consistent and explainable if we allow that there hasn't been very much time. But if we allow that there are millions of years, such as the data we get from radiometric dating, then you can't understand why these sedimentary structures are still there. Why haven't the burrowing of animals and other forces changed the internal structure of the layers? So this is a big mystery that our understanding of time offers a solution to that is not explainable in terms of long ages of time. And there are other things like that. For example, a layer that I study in Utah, it has supposedly 10 to 30 million years missing between two layers, and yet it's perfectly flat. There's been no erosion before the layer was put on top, and yet there's supposed to be 30 million years. Well, 10 million years is enough time to erode all of North America away to sea level. And if you had 10 million years and nothing's happening, how do you explain that? There is evidence that the material underneath was still soft. It was not consolidated. This is evidence because the overlying material has pushed down into it. And this could only happen if it was still mud. It wouldn't happen if it had been turned to rock. So we can see that there wasn't enough time for the layer to become hard like rock. It was still soft and muddy. But if it was soft and muddy for 10 million years, why didn't it erode away? And so we have an enigma. But if we consider that the time wasn't millions of years, but maybe was very quick, then we can understand and explain that.
Conventional geologists think that there are millions of years passing as these layers are deposited, one on top of the other. Those of us who take the Bible account seriously, we don't see those millions of years being there. We don't believe there were millions of years. We don't believe there was that much time. There's still some time that passes. It's been thousands of years since creation. But how do we deal with this difference, thousands of years compared with millions of years? One of the things that happens is, if you are a conventional geologist, you have come to believe firmly that there were these millions of years. You look at the rocks and you automatically interpret them that way, as forming very slowly. Maybe there were catastrophes, but lots of time passing in between. But those of us who take the Bible seriously, we see it differently, and we will look for things and ask questions that the conventional geologist doesn't ask. The Bible actually opens our minds and opens our eyes to see things that other people are not noticing, to ask questions that others are not asking. When we do that, we discover things that a conventional geologist probably won't even notice. We ask questions that they're not likely to ask, because it wouldn't mean anything in their point of view.
If you have a mind that is closed to certain possibilities that are not unreasonable, but maybe are outside the purview of whatever discipline you're working in, you will not think of certain ways of explaining the world around you. One of the advantages I have as a Christian geologist who believes in the biblical account of origins is that I can look at things on a broader perspective. I can consider not only the explanations of standard geologists, but I can consider a whole perspective beyond that, which involves catastrophic processes on a global scale. And when I do that, and I look at the rock record in those terms, I can see explanations that other geologists wouldn't think of.